All right, let's take a look at examples 4 and 5, which are going to be related. So in the previous cases, we just gave the formula. For examples 4 and 5, we're going to look at the relation in terms of geometry that you've already looked at. So the formula C is equal to 2 pi r expresses a relationship between the circumference and the radius of a circle. If the radius is increasing at a certain rate, what happens to the circumference? Well, if the radius is increasing, then the circumference, because of the relationship, is also going to be increasing. Now, I should note that some of the geometry formulas are going to be on your formula sheet. This one is not on your formula sheet. Some of them you should just know from previous courses. So it says the radius and the circumference are implicit functions of time and therefore will differentiate implicitly to determine the relationship between the rates of change. So if my formula is C is equal to 2 pi r, and I'm figuring out what's happening to the circumference in relation to time, then when I differentiate, I'm going to get dc over dt is equal to 2 pi, and then the differentiation for r in terms of time is just dr over dt. The relationship indicates that the rate of change of the circumference with respect to time is equal to 2 pi times the rate of change of the radius with respect to time. All right, let's see how that works in practice, taking a look at example 5. So a circular ring is heated so that it expands. If the rate of increase of the radius is 0.1 centimeters per second, so that's the rate relationship with respect to time, determine the rate at which the circumference is increasing. So because this is our relation or radius with respect to time, this is also going to be our dr over dt is equal to 0.1 centimeters per second. So when we think of what we need to do for those full marks, the first one is we're going to define the variables and draw a diagram. So what do we know? We know that the formula is C is equal to 2 pi r in terms of the relation of a circumference to the radius. We know that C is our circumference. We know that r is our radius. And we also know that we're doing this with respect to time. We can state what the restrictions are. C and R both have to be greater than 0, otherwise the circle wouldn't exist, and time has to be greater than or equal to 0. And as we already stated, we know that dr over dt is 0.1 centimeters per second. Now, it doesn't have to be an overly complex image. We know that for a circle, we're just dealing with a circle where the radius is going to exist here. And if you want, you can indicate that wrapping around is the circumference. It's the perimeter of that circle. what we're trying to find is dc over dt. So what are we going to do? We're going to differentiate that formula in terms of time. So dc over dt is equal to 2 pi and dr over dt. What we're trying to solve is that dc over dt, and we know what dr over dt is, so we're just going to substitute in. Which means that my dc over dt is going to equal 0.2 pi. And that is measured in, the measurement for the circumference is in centimeters, and it's in relation to seconds. Always make sure you put the units back in here. And then we can make our statement. Therefore, the circumference of the circular ring is increasing because it has a positive rate at a rate of 0.2 pi centimeters per second. For example 6, it says, if we know that the radius is increasing at a rate of 2 centimeters per second, find the rate of change in the volume of a spherical balloon when the radius is 10 centimeters. So what do we have? We have a balloon. I know it's almost impossible to draw a sphere that doesn't just look like a circle, where I have the radius is going to exist in here. What do we know about this balloon? Well, we know that the volume of a sphere is 4/3 pi r cubed. That is on your formula sheet. We know that V is volume. We know that R is a radius. And we know that T is time, because this is in relation to time, where the volume and the radius have to be greater than 0, and the time has to be greater than or equal to 0. We also know, based on what it has told us, that in this case, the dr over dt, the radius in the relation to time, is 2 centimeters per second. And we know that the radius at this point is 10 centimeters. What is it we're trying to solve? We're trying to solve dv over dt. So, just like in the previous example, we are going to start by differentiating in terms of time. So if v is equal to 4 over 3 pi r cubed, then that means that dv over dt is equal to 4 over 3 pi times 3 r squared times dr over dt. And that times by 3 and divide by 3 are just going to cancel each other out. We still know that this is all when r is equal to 10. So we're going to sub into that differentiation and say that dv over dt is equal to 4 pi times r squared or 10 squared times dr over dt, we already know is 2, which means that dv over dt is going to equal 800 pi. And because this is in a volume and my radius was in centimeters, my volume would be in centimeters cubed. And this is in relation to the time, which is being measured in seconds. And then we can state, therefore, the volume of the balloon is increasing at a rate of 800 pi centimeters cubed per second when the radius is 10 centimeters.